To accurately apply correction factors at the bottom of the 310.16 table, firstly determine the conductor size and type. In this case, it's 3500 type TW copper. Secondly, determine the insulation rating, which is 60-degree insulation. Thirdly, determine the conduit type. The conduit is rated for 320 amps. Then find the applicable correction factors from 310.16. The number of conductors in the conduit is 3. The raceway type is in conduit. The ambient temperature is 77 degrees Fahrenheit and the conductor temperature rating is 60 degrees Celsius. The correction factors are as follows. For the number of conductors in conduit, the correction factor is 0.8. For the raceway type, the correction factor is 0.8. For the ambient temperature, the correction factor is 1.2. To calculate the adjusted ampacity, multiply the initial ampacity by all applicable correction factors. In this example, it's 320 amps times 0.8 times 0.8 times 1.2, which equals 262 amps. The ambient temperature under the store concrete is not specified. However, it is likely to be cooler than the ambient temperature at the bottom of the NDP, as the concrete mass will act as a thermal sink. Assuming the store will have air conditioning set at 74 degrees Fahrenheit, it is reasonable to estimate that the ambient temperature under the concrete may be around 70 degrees Fahrenheit. To calculate the adjusted ampacity at 70 degrees Fahrenheit, use the same correction factors as before, but with an ambient temperature correction factor for 70 degrees Fahrenheit, which is 1.5. So 320 amps times 0.8 times 0.8 times 1.5 equals 277 amps. The adjusted ampacity at 70 degrees Fahrenheit, 277 amps, is still below the minimum circuit ampacity because of the air handling unit, which is 338 amps. However, it is important to note that this calculation does not account for any potential temperature rise in the conduit due to the increased load. To determine if pulling new wire is necessary, additional calculations or measurements would need to be performed to verify the conduit temperature remains within acceptable limits under the increased load. This may involve using a temperature probe or performing a heat loss calculation. To elaborate on ampacity correction and adjustment factors, let's delve deeper into the NEC guidelines and real-world considerations. Ampacity refers to the maximum current in amps a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Table 310.16 of the National Electrical Code (NEC) provides the allowable ampacities for insulated conductors rated up to and including 2000 volts, 0 to 2000 volts, and not more than 3 conductors in raceway or cable or earth, directly buried based on ambient temperatures of 30 degrees Celsius, 86 degrees Fahrenheit. These ampacities are based on specific temperature ratings of the conductors such as 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. However, in practical applications, several factors can affect a conductor's ability to dissipate heat, leading to the need for correction and adjustment factors. Firstly, ambient temperature correction. Ambient temperature is the temperature of the environment immediately surrounding the conductor. If the ambient temperature is higher than the 30 degrees Celsius, 86 degrees Fahrenheit reference point in Table 310.16, the conductor's ampacity must be derivated using correction factors found at the bottom of the table. These factors reduce the allowable ampacity because higher ambient temperatures reduce the conductor's ability to dissipate heat, thereby increasing its operating temperature. For example, if the ambient temperature is 40 degrees Celsius and you're using a conductor with a 75 degrees Celsius insulation rating, you would find the corresponding correction factor, say 0.88, and multiply it by the conductor's base ampacity from Table 310.16. This gives you the adjusted ampacity for that specific ambient temperature. Secondly, number of conductors adjustment. When multiple current-carrying conductors are bundled together in a raceway, cable, or directly buried, the heat generated by each conductor can raise the overall temperature within the enclosure. This mutual heating effect reduces the ability of each conductor to dissipate heat effectively. To account for this, the NEC requires the ampacity of each conductor to be adjusted based on the number of current-carrying conductors in the raceway or cable. Adjustment factors for the number of conductors are provided in Table 310.15b3 of the NEC. For instance, if you have 7 to 9 current-carrying conductors in a raceway, the adjustment factor might be 0.7. This means that the ampacity of each conductor must be reduced to 70% of its value from Table 310.16 after any ambient temperature corrections have been applied. It is important to note that equipment grounding conductors and bonding conductors are generally not considered current-carrying conductors for ampacity adjustment purposes. Neutral conductors are only considered current-carrying conductors if they carry a significant unbalanced load, such as in a 3-wire circuit with a high percentage of nonlinear loads. Thirdly, termination temperature limitations. Conductors are connected to equipment such as circuit breakers, transformers, and receptacles at termination points. These terminations are typically rated for a specific maximum temperature, such as 60 degrees Celsius or 75 degrees Celsius. The NEC requires that the conductor's ampacity be selected based on the lowest temperature rating of any connected termination, conductor, insulation, or device. For example, if you are using a conductor with a 90 degrees Celsius insulation rating but connecting it to a circuit breaker with a 75 degrees Celsius termination rating, you must use the ampacity corresponding to the 75 degrees Celsius column in Table 310.16. This ensures that the termination does not overheat, which could lead to insulation degradation, equipment failure, or even a fire hazard. Fourthly, application of correction and adjustment factors. The NEC provides specific guidelines on how to apply correction and adjustment factors in various scenarios. The general rule is to apply all applicable correction and adjustment factors in a sequential manner to determine the final allowable ampacity of the conductor. Firstly, determine the base ampacity from Table 310.16 based on the conductor size and insulation type. Secondly, apply any ambient temperature correction factors. Thirdly, apply any adjustment factors for the number of current-carrying conductors. Fourthly, ensure that the final ampacity does not exceed the lowest temperature rating of any connected termination, conductor, insulation, or device. For example, let's say you have a number 12 American wire gauge AUG copper conductor with a 75 degrees Celsius insulation rating installed in a raceway with 6 other current-carrying conductors in an ambient temperature of 40 degrees Celsius. The base ampacity from Table 310.16 for a number 12 AWG copper conductor with a 75 degrees Celsius insulation rating is 30 amps. The ambient temperature correction factor for 40 degrees Celsius is 0.88. The adjustment factor for 7 to 9 current-carrying conductors is 0.7. Therefore, the adjusted ampacity would be 30 amps times 0.88 times 0.7, which equals 18.48 amps. However, if the terminations are only rated for 60 degrees Celsius, the ampacity would be limited to 20 amps from the 60 degrees Celsius column in Table 310.16. So, the final allowable ampacity in this case would be 18.48 amps, as it is less than the 60 degrees Celsius termination rating. The NEC provides specific requirements for conductor sizing and overcurrent protection to ensure the safe and reliable operation of electrical systems. Proper application of correction and adjustment factors is essential for selecting conductors with adequate ampacity for the intended load and operating conditions. Failure to properly apply these factors can lead to conductor overheating, insulation degradation, equipment failure, and potentially hazardous conditions. In addition to the NEC guidelines, there are other factors to consider when selecting and installing conductors. Firstly, voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction, reduce lighting levels, and increase energy consumption. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be sized large enough to carry the load current without excessive voltage drop. Secondly, conductor material. Conductors are typically made of copper or aluminum. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. However, aluminum is lighter and less expensive than copper. When selecting conductor material, consider the conductivity, weight, cost, and corrosion resistance of each material. Thirdly, environmental conditions. Conductors may be exposed to various environmental conditions, such as moisture, chemicals, and extreme temperatures. Select conductors with insulation and jacketing materials that are suitable for the specific environmental conditions. For example, conductors installed in wet locations should be listed as suitable for wet locations. Fourthly, installation methods. The way conductors are installed can affect their ampacity and heat dissipation capabilities. Conductors installed in free air typically have a higher ampacity than conductors installed in raceways or cables. Ensure that conductors are installed in accordance with the NEC and manufacturer's instructions. To further clarify the calculations, consider the scenario: a 100 amp feeder supplies power to a subpole located 100 feet away. The load consists of non-continuous loads. The conductors are number 3 American wire gauge, AUG, copper with THHN insulation installed in a steel conduit. The ambient temperature is 35 degrees Celsius. There are 4 current-carrying conductors in the conduit. The terminations are rated for 75 degrees Celsius. Firstly, determine the base ampacity. From table 310.16, the base ampacity of number 3 AWG copper conductor with THHN insulation is 100 amps at 75 degrees Celsius. Secondly, apply ambient temperature correction. The ambient temperature is 35 degrees Celsius. Correction factor from table 310.16 is 0.91. The corrected ampacity is 100 amps times 0.91 equals 91 amps. Thirdly, apply adjustment factors for the number of conductors. There are 4 current-carrying conductors in the conduit. The adjustment factor from table 310.15b3 is 0.8. The adjusted ampacity is 91 amps times 0.8 equals 72.8 amps. Fourthly, check termination temperature limitations. The terminations are rated for 75 degrees Celsius. The adjusted ampacity of 72.8 amps is less than the 75 degrees Celsius ampacity of 100 amps for number 3 AWG copper conductors. Fifthly, check voltage drop. The voltage drop should be checked to ensure it is within acceptable limits. If the voltage drop exceeds 3%, the conductors may need to be upsized. In this case, the adjusted ampacity is 72.8 amps. This is less than the 100 amp overcurrent protection. Therefore, the number 3 AWG copper conductors are not suitable for this application. The conductors need to be upsized to handle the load and the overcurrent protection. The proper application of ampacity correction and adjustment factors is essential for ensuring the safe and reliable operation of electrical systems. Failure to properly apply these factors can lead to conductor overheating, insulation degradation, equipment failure, and potentially hazardous conditions. The National Electrical Code, NEC, provides specific guidelines for conductor sizing and overcurrent protection to ensure that electrical systems are installed in a safe and workmanlike manner. Always consult the latest edition of the NEC and follow the manufacturer's instructions for selecting and installing conductors. Now let's focus on some practical considerations. In real-world applications, several factors can influence the accuracy of ampacity calculations and the overall performance of electrical systems. Understanding these factors is essential for ensuring that conductors are properly sized and installed to meet the demands of the connected loads. Firstly, load characteristics. The type of load connected to a circuit can significantly affect the current flowing through the conductors. Continuous loads, such as lighting and heating, draw current for 3 hours or more. Non-continuous loads, such as motors and appliances, draw current for less than 3 hours. The NEC requires that conductors be sized to carry 125% of the continuous load plus 100% of the non-continuous load. This ensures that the conductors can handle the additional current drawn by continuous loads without overheating. Secondly, harmonic currents. Nonlinear loads, such as electronic devices and fluorescent lighting, can generate harmonic currents. Harmonic currents are currents with frequencies that are multiples of the fundamental frequency, typically 60 Hz. These harmonic currents can cause overheating of conductors, transformers, and other electrical equipment. To mitigate the effects of harmonic currents, conductors may need to be oversized or special harmonic filters may need to be installed. Thirdly, conduit fill. The percentage of a conduit's cross-sectional area that is occupied by conductors is known as the conduit fill. The NEC limits the maximum allowable conduit fill to prevent overheating of conductors and to facilitate the pulling of conductors into the conduit. The conduit fill requirements vary depending on the type of conduit, the number of conductors, and the size of the conductors. Exceeding the maximum allowable conduit fill can lead to conductor overheating, insulation damage, and difficulty in pulling conductors. Fourthly, voltage stability. Maintaining stable voltage levels is crucial for the proper operation of electrical equipment. Voltage fluctuations can cause equipment to malfunction, reduce lighting levels, and increase energy consumption. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be sized large enough to carry the load current without excessive voltage drop. In addition to the NEC guidelines, there are other practical considerations to keep in mind when selecting and installing conductors. Firstly, future expansion. When designing electrical systems, it is important to consider the potential for future expansion. Conductors should be sized large enough to accommodate any anticipated increases in load. This can help avoid the need for costly and disruptive rewiring in the future. Secondly, accessibility. Conductors should be installed in locations that are easily accessible for maintenance and repairs. This can help facilitate troubleshooting and minimize downtime in the event of a problem. Thirdly, labeling. Conductors should be properly labeled to identify their purpose and destination. This can help prevent confusion and ensure that circuits are properly connected. Fourthly, workmanship. The quality of workmanship is essential for the safe and reliable operation of electrical systems. Conductors should be installed in a neat and professional manner with proper connections and support. Poor workmanship can lead to loose connections, insulation damage, and other problems that can compromise the safety and performance of the electrical system. Also, the condition of existing infrastructure is important. When working with existing electrical systems, it is important to assess the condition of the existing infrastructure. This includes inspecting conductors, conduits, and equipment for signs of damage or deterioration. Any damaged or deteriorated components should be replaced or repaired to ensure the safety and reliability of the electrical system. The NEC provides comprehensive guidelines for conductor sizing, ampacity correction, and overcurrent protection. However, practical considerations such as load characteristics, harmonic current, conduit fill, and voltage stability can also play a significant role in the performance of electrical systems. By considering these factors in addition to the NEC requirements, electrical professionals can ensure that conductors are properly sized and installed to meet the demands of the connected loads while maintaining a safe and reliable electrical system.